Alright, so in this lesson we're going to be looking at phase changes and states of matter. Alright, so we're going to have a brief warm-up question here. Excuse me, three brief warm-up questions. First, when a substance changes states of matter, i.e. from a solid to a liquid or a liquid to a gas, what happens to the temperature of the substance? 2, draw a graph showing temperature versus heat added as water changes from ice to liquid to gas. Okay? And then lastly, why is a pool cooler than the surrounding air if they both receive the same amount of heat from the sun? Take a moment to answer these questions and we will move on with our lesson. Alright, so 6.3, phase changes and states of matter, that's what we're looking at today. Okay, so no immediate announcements, no immediate quizzes or anything that's coming up in next week. What we're up to today, what are the different states of matter? Alright, this is something we've learned about in prior science classes before, but we're going to dig a little bit deeper than prior science classes. What is a phase change? What happens when one occurs? Alright, again, a little typo right there. And how do pressure and temperature affect when a phase change occurs? Okay? And how can we predict based on pressure and temperature when a phase change will occur? So here are the standard non-quantum states of matter. There are more states of matter if you dive into the world of quantum mechanics, but we're not going to be there yet. Alright, so there are gases, liquids, solids, and then plasma. Gases, liquids, and solids we're going to look at in detail in today's lesson. Plasma we'll look at a bit, but plasma is better reserved for later units. Okay? So name for phase changes. Okay, so please make sure you get this chart down right here. This shows the names for all the phase changes that we're going to be looking at today. Okay, so if a solid goes to liquid, that's melting, and if a liquid goes to solid, that's freezing, like we know with water. If liquid turns into a gas, that's vaporization. All right, like water vapor is a gas. All right, and then if we go from a gas to a liquid, that's condensation. All right. Called as such because gas condenses back down to a liquid. Okay, so please make sure you have these four phase changes. Okay, recombination, ionization, you do not have to worry about. Okay, and then we do have a change of state of matter from a solid to a gas or a gas to a solid without ever going through a liquid phase. And when that happens, when a solid goes to a gas, we call that sublimation. And then when a gas goes straight to a solid without becoming a liquid, we call that deposition. Okay? Sublimation we've actually already seen before when we made our dry ice bomb, when the frozen CO2 we put at room temperature turned directly into a gas. That was an example of sublimation. Alright, so here at this point we would typically do a lab, but we're not in a lab here. But the basic premise of the lab would be to record the temperature every minute or so while a sample of ice turns from ice to liquid to gas, and then recording what the temperature is at all points, plotting those temperatures, and seeing if you notice any unique or interesting or unexpected trends. Okay? Alright, so here is what would happen if you collected your lab results here, okay? So, we can see right here, alright, that instead of having, when our water changes from ice to liquid to gas, okay, we're not just having a direct increase in temperature. We can see there are times when our temperature plateaus out, alright, such as right here from about 2 minutes to about 9 minutes, and then from right here from about 25 minutes onwards, okay? So what's happening at these points, alright? So at these points right here, our temperature plateaus out. What you would see is that this occurs during a phase change. When you go from a solid to liquid, such as right here, when ice turns to water, or when you have a liquid turn to a gas, such as right here. So the reason why this happens and what we're about to explore in greater detail, okay, is that at these points, energy that's being added in the form of heat is being used to break chemical bonds and weaken chemical bonds instead of raising temperatures. Better said, not chemical bonds, most likely intermolecular bonds, but still the same idea. Okay, so energy at this point that's added in the form of heat is not being used to raise temperature, but instead using to weaken intermolecular bonds and thus cause us to undergo a phase change. Okay. So phase changes. How to explain phase changes within the context of kinetic theory? So a phase change is a change of state of matter, i.e. like freezing or vaporization, or if you go in the opposite direction, melting or condensation. So a phase change occurs when the energy added to a substance causes intermolecular bonds to weaken. So when we're solid, our molecules can't move around a lot, hence why solids tend to have a fixed, rigid shape, okay? And that's because there's these intermolecular bonds that's holding the molecules in place. So when we add heat or energy to a substance that causes a phase change to occur, these intermolecular bonds are being weakened to the point that now we have something like water, where intermolecular bonds are weaker. Our water can move around. It can take on different shapes. And then we have, if we continue adding heat, those intermolecular bonds are going to be eliminated to the point that our water molecules can move around freely, which is when we have a gas. So phase changes in kinetic theory part 2. Okay? So when an object reaches a phase change, i.e. a freezing or boiling point, heat is used to break/strengthen chemical bonds, intermolecular bonds instead of raising temperature. So right here, all right, so right here we're going to have heat being used to melt our solid ice instead of raising the temperature. And then at point D right here, we're going to have heat being used to turn our water into a gas, turn from liquid into a gas, okay? So at a phase change, there's a mixture of states of matter, a transitioning period, okay? So what's interesting to note is you may have learned about endothermic and exothermic reactions before, okay? So when our solid is turning to liquid, when we're undergoing melting, there's going to be a brief raise in temperature for our substance, and then when it's undergoing the phase change, there'll be no raise in temperature, and then afterwards, there'll be a rise in temperature again. So that would be an endothermic reaction because we're absorbing heat. Our substance is absorbing heat, okay? Whereas if we are going from a liquid to a solid now, aka we're freezing, so we're freezing, let's say, water now, okay, that would be an example of an exothermic reaction where heat is released by the substance. All right, heat is released by a substance, which causes the substance temperature to decrease to the point that it undergoes a phase change, okay? And then once it's undergone a complete phase change, the temperature will continue to decrease as more heat is given off by the object, okay? And so a useful way to think about these phase changes on a molecular level is in terms of thinking of molecular bonds as springs. In physics, we model chemical bonds and intermolecular bonds as springs. So what's happening here is when you add heat to these molecules, the intermolecular bonds, the springs, get more bouncy and undergo stronger oscillations or stronger cycles of motion up until the point where we stretch our spring out too much, like what happens in real life, and we can't get the well, better said, not that we can't get the spring back, but that the intermolecular bonds have weakened. The spring has weakened by stretching out too much. Now, the only difference between this and real life is in real life, if you stretch out spring too much, it's completely ruined. It can never be returned. Whereas with intermolecular bonds, the spring can be returned back to its original state. And that's when we have a phase change going on from, say, a liquid to a solid, or from a gas to a liquid. So here's our summary of results, okay, state of matter and then phase change, okay. When we have a state of matter, we start off as a solid, the chemical bonds are strong. All right, and then we have a phase change when we're going freezing or melting. If we're freezing, the chemical bonds are strengthening, meaning that heat is being released. Okay, remember heat is used to break and weaken the chemical bonds. So heat is being released when we're freezing, causing the chemical bonds to re-strengthen. Okay, when we're melting, that means heat's being added to the chemical bonds, which is weakening chemical bonds, and thus forcing our substance to undergo a phase change from a solid to a liquid. Okay. Now, if we have a state of matter that's a liquid, the chemical bonds are weak, but they're still kind of there, just not as much, okay? And in that case, next phase change we're going to go is a condensation, which means you're going from a gas to liquid, or vaporization, a liquid to a gas, okay? So in this case, when we have condensation going on, that means we're going from gas to liquid, which means our chemical bonds are strengthening, they're reforming, okay? So as a result, we're going to go from a gas to a liquid. Whereas for vaporization, if we go liquid to a gas, that means heat is being absorbed by our object, which is weakening the chemical bonds of our object, which causes vaporization to occur, like when we have water going to a gas. Okay? And then lastly, if we have a gas, there's no bonds. The particles are free to move, which is why you see gas being able to expand and contract at will, depending on the container that's in. And let me go back right here, actually. I forgot to show you guys the simulation here. So this is a Ck12 demonstration that's going to show you guys what's happening right here when we undergo these phase changes. Okay, so see how we have a solid right now? Our molecules are very rigid. They can move a little bit, but not too much, and they're stuck together by these intermolecular bonds. So we can see right here that temperature rises, and then as we undergo a phase change, the temperature is not rising because that energy, the heat energy, is being used to weaken the chemical bonds. Okay. So now all of our chemical bonds have been weakened. We can start causing our temperature to rise again. The temperature will continue to rise until we reach about 100 degrees Celsius, which is the boiling point of water, 212 degrees Celsius, 212 degrees Fahrenheit, which at this point right here, the heat is not going to be used to raise the temperature. The heat is going to be used to cause a complete liberation of our water molecules, breaking off all the chemical bonds in the water molecules. So now we have vaporization. We can see the boiling of the water. We can see the steam being given off. And so at this point, heat is being used to cause that phase change. Our water is turning into a gas. So instead of temperature increasing, that heat's being used to turn water into a gas. And now we can see our temperature starts to rise again. So that's a nice little demonstration of what we've been looking at in this lesson here. And then in terms of visualization, all right, in terms of visualization here, here's what our substance looks like at a molecular level at each point in our graph. So this would be A right here when we're solid. All right, chemical bonds are strong, rigid. Our molecules are not going to move a whole lot. Then we have a B where we undergo a phase change. All right, so nothing's really shown for B. It's kind of transition from A to C. All right. And then we have C, where our water molecules are more free. The molecular bonds, intermolecular bonds, are weakened, but not completely so, not as much as a gas. And then at D, we have another transition from liquid to gas. And then from E, and then at E, we're completely liberated. All our intermolecular bonds are weakened, and thus our molecules are free to completely move of their own accord. All right, so now we move into the specific heat of an object, all right? So we may have noticed before that some objects get hotter than other objects quite easily, okay? Say if we leave a metal cup and styrofoam out in, say, the hot Arizona sun for an entire day, we'll notice that the styrofoam, yes, may get hot, but the metal cup is something we definitely don't want to touch. So why does this happen? Why is it that some materials heat more easily than others, okay? Or undergo a change in temperature more easily than others, okay? So the reason why is that different chemical compositions of substances means that some substances require more heat than others for a temperature change to occur. All right, the specific heat of a substance refers to the amount of heat required to change the substance's temperature by 1 degree Celsius. So the higher amount of specific heat you have, that means there's more heat required to change the substance's temperature, and thus it's more difficult to raise the temperature of that substance. Okay? Now, if you want to know what's happening with the chemical compositions at a more in-depth level that causes this specific heat, that goes into quantum mechanics and solid-state physics and statistical mechanics, condensed matter theory. Stuff that, oh boy, I'd love to go over, but that's out of our league for right now. All right, so objects with lower/higher specific heat can tend to conduct heat better/worse, typically speaking, okay? So for example, something like iron, which we would expect to conduct heat well, has a lower specific heat, meaning that it takes less heat to raise the temperature of iron by 1 degree Celsius. Whereas something like liquid water, which doesn't conduct heat very well, has a specific heat of 4.18 joules per gram degree Celsius, which means that the amount of heat required to raise liquid water by 1 degree Celsius is greater than the amount of heat required by iron. So as a result, iron tends to conduct heat better than liquid water, okay? Typically, there are some exceptions to this, but we're not going to go into the exceptions. All right, so referring back to our opening question, let's say we have a pool or let's say we have a pool and then we have the concrete sidewalk around the pool or surrounding air. Why is it that the pool would be cooler than, say, the concrete sidewalk or the surrounding air? Please take a moment to think and answer on the basis of specific heat, and use the chart at right to justify your answer. So if we look here, we see that liquid water has, again, a specific heat of 4.18 joules per gram degree Celsius, whereas dry air has a specific heat of 1.01 joules per gram degree Celsius. So as a result, we're going to require less heat to raise the temperature of dry air 1 degree Celsius than we are for liquid water. So as a result, if dry air and liquid water are receiving the same amount of heat from the sun, then dry air is going to undergo a greater change in temperature than liquid water. Okay? Now, what about concrete? We don't see concrete up here. Where is concrete? All right? So concrete, yes, is not listed at this table right here, but because we know that concrete will be a lot hotter than a pool on a hot summer day, that tells us that the concrete must have a lower specific heat than liquid water, since concrete is able to undergo a greater change in temperature for the same amount of heat from the sun. All right, and here's our official response, just for bookkeeping purposes. If you want to take a moment to get that down, you can. And we are going to move on to our next topic here. All right, so pressure and temperature graphs, okay? So it actually turns out that the temperature at which something undergoes a change in state of matter is not just one single point for one object, but it can depend on the pressure of your substance, okay? So as pressure and temperature are related, the pressure of an environment will affect the temperature at which a phase change occurs, okay? Generally, as pressure increases, so too does the temperature at which phase changes occur, all right? So if we look right here, if we want to go from say solid to liquid for, let's say, water, I believe this is the graph for water, all right, we can see that as pressure increases, the temperature also slightly increases as well. The reason being that typically higher pressure means that more molecules are more compact and thus more likely to keep a state of matter. Okay, it's hard to make them undergo a change of state of matter. Now, there are exceptions to this rule here, as there are exceptions to all things. Not all substances play by our rules, and that's a quite unique aspect of physics and chemistry, is figuring out why those substances don't play by typical rules that other substances play by. But for right now, we're going to focus on the standard rules, which is that at higher pressure, molecules are more compact and thus more likely to keep a state of matter. Okay? So if you look right here, there's this interesting point called triple point here where we can see these three areas intersect, solid, liquid, and gas. Well, you would guess it, and you would be correct, that this is a very weird phenomenon where we have both solid, liquid, and gas coexisting at the same time. So most materials, I can't actually say for certain each material, I'm not a chemist here, but most materials do tend to have a triple point, a unique temperature and pressure at which all three states of matter exist at once. Okay? So let's take a look at this triple point in a video right here. If our video wants to load. Yep, so if we look here, it seems kind of gelatinous, which is very, very weird. It seems gelatinous right here. We can see it does this kind of like gelatin-like motion right here. But what you can see is that this is where we have our triple point at. We can see we still have ice here. And look, the ice isn't melting. The ice isn't melting. It remains the same shape, remains the same size, okay? But we can see now that we have water, okay? And we also have the water boiling, okay? So we have water boiling, we have ice, and we have liquid water. So we have all three states of matter existing at this particular pressure and temperature, which is pretty dang cool. All right, so we can see we can still have the ice, and now we have all these bubbles gathering around it right here. All right. So look what's happening right here. We can see there's freezing going on right here. We can see there's boiling going on. All right. We can see that there's melting. If we look, the ice was starting to change. So this is just absolutely crazy right here. All right. In fact, it actually kind of reminds me of like pancake batter when you're making pancakes, oddly enough. Yep. But again, we can see how there's freezing. We see how there's freezing. We can see the frost around the edges. But we can see there's also boiling going on right here. All right, so pretty weird stuff. All right. So a quick check for understanding here. At high altitudes, especially in the Andes, a mountain range in South America, it is known that water will boil at lower temperatures. Please explain why this is so. So at high altitudes, the atmospheric pressure decreases, okay? As a result, the boiling point of water will lower as water molecules are less likely to stay connected due to weaker intermolecular bonds. Well, better said, not weaker intermolecular bonds, but we know that because of the decrease in pressure, we know that the boiling water is going to be less compact. Pressure presses down on the water, okay? So as a result, the molecules are less compact. They're going to be less likely to stay together. So the boiling point of water will lower as a result. And then last week we come to our last state of matter. Again, we're going to reserve this for electricity and magnetism because that's when plasma is more properly explained. All right. So plasma, if a substance becomes heated enough, electrons will be stripped from the substance's atoms and become free. Okay. The atoms without electrons are called ions. Perhaps you learned about this in chemistry, okay? Ionized gases are gases that either have gained electrons more than they usually have or are stripped of their electrons, okay? So the mixture of ions and free electrons is called plasma, And then ionization is when gas becomes a plasma because we're turning our atoms into ions, we're stripping electrons away. And then recombination is when plasma becomes a gas again. The reason why we call it recombination is because the electrons are recombining with the atoms. All right, and this is our lesson on states of matter.